Hi everyone and beloved Professor Nafis Ahmed Chisti. Today I discuss on how to build up a digital working control system. First of all, they have here a question. We see that they want to know prepare a design to monitor available space in a parking garage that can house up to P plus F plus cars. That means according to my ID, it is a car limitation or maximum car of the garage. Okay. Then they say that when the garage is full of cars, it continuously displays the word full. Okay. Otherwise, it will display space available in a blinking fashion through another display sign with the 7 segment display. Okay. Here they given a block diagram. Keep it obviously user defined from output, then encoder. Its prime work is decimal to binary, then register, then comparator, then connection additionally timer circuit 1, timer circuit 2, etc. Now my task is to first of all they have want to know outline the essential steps, the appropriate sequence to develop a block diagram and a flow diagram for designing a automated parking control system as described above. Okay. If car is full, then 7 segment display show full, or car is not full, then 7 segment display space available based on a sensor data collected at the entry and exit points. Okay. Then use a counter to collect sensor. Okay. Then show the internal architecture of the counter. How flip-flop are connected to from the counter. Now I going to my original circuit that I have been doing myself. My ID 235211192. According to my ID, space available in parking garage or maximum car limitation is 6. First of all, I create a block diagram. Keep it obviously output from user, then encoder, keep it decimal to binary, generate, then register. I used CPU, that means serial input, parallel output. Then I used the comparator 3-bit, timer 1, timer 2. If display is full, then 7 segment display full, choose full display. Display is not full, 7 segment display showing space available or blink. Then clock generate pulse up down, that's why space available with blinking. Then here connected a entry and exit point. Then I create a flow diagram just like a programming language, C++ or C. However, start, read, keep at maximum 6, detect anti sensor. If anti sensor detect, then yes, increment counter or up counter. If detect exit sensor, then yes, decrement sensor or down counter. And after that compare with max. Is count equal max? Yes, full. No display available. Repeat. Encoder designing. Digit 10 is given as input to the encoder by user. Input kept and maximum car limitation is 6. The logic, I designed a 4-bit encoder to translate the maximum decimal 6 to maximum binary 0, 1, 1, 0. I derive the output function based which decimal are pressed. Okay, here I trying to show my logical expression by numbering system. Noted that allows to maximum capacity 6 from keypad. Above I show user given decimal given number convert binary using a encoder. Okay, logical expression here I show that y3 equal 0, no input. Y2 is high when input I4 plus I5 plus I6 is activated. Then Y1 is high, then I2 plus I3 plus I6 is activated. Then Y0 is high, then I1 plus I3 plus I5 is activated. Now here is my simple logical expression. Now I use register SHIPU register, that means serial input output parallel. It pushes the data enters one bit at a time serially and is shifted and into the register by a clock pulse. Here my goal is once all bits are shifted in, they are available parallelly on 4 output lines. This provides a constant reference value. Now here I elaborately discuss on some point that encoder gives 4-bit binary output. To store and use this 4-bit input inside digital system, we need register. CPU register can take serial input. That means input 1 bit per clock and store 4 bits, then output 4 bits at the same time. Then point number 4, after 4 clock pulses, output becomes parallel Q1, Q0, Q1, Q2, Q3. And it is my CPU register internal architecture for 4-bit. And clearly we see that now I need to a comparator. I need to a comparator. The comparator checks the status of garage is comparing input A. Here input A current from the counter and input B the value from the register. Again I saying that here input A current from the counter and input B current from the register. Okay, here we see that theory logic. First of all, A equal B. If A equal B, count reaches 6, the equal to output goes high. The trigger the full indicator and stops every gate from opening. That means monostable circuit activate and close the gate. And A less than B, if the count is less than 6, the less than output is high. That means a stable circuit is activated and 7-segment display shows that space available with blinking. Okay, here I last step is I used a up down counting, and it is a simple logic circuit. When a car enters, a sensor sends pulse to up pin and updating number 1. If I see that 0 0 0, that means 0 present count. If one car empty, then counter updated value is 0 0 1. Then another car is empty 0 0 1 to 0 1 0. Then another car is NT 0102 and it is a continuous process until car number is maximum according to my ID 6. And opposite counter is down counting. That's why first of all I assume that my garage is full. That means my garage uh, has 6 cars already. Then if cars is exit, first of all full, that means binary 6110 present count. If one car exists, the new updated value is 101, that means 5. And another car is exit, that means 100, that means 4. Another car is exit 010, that means 3. Another car exit 001, that means 2. And it is continuous process until or unless 0. Okay, here I trying to show a synchronous 3-bit up-down counter. 3-bit synchronous up-down counter. Yeah. Here we see that two circuit, one is stable, another is unstable. A unstable timer we used for gate control, and on stable timer is we used blinking, and it is a simple process. When a car is empty, then unstable circuit is activated and gate open. When car of full of garage, then a stable circuit is active, then gate is totally off and blinking 7-segment display shows space available. Okay, now it is my second question. I back to original question given from my faculty. Okay, second question. They said that design a circuit to activate the two 7-segment displays using two 555 timers. One circuit to display full, another to display space available. When garage is full cars, it should continuously display full. Okay. When garage is not full, then display shows space available in blinking fashion. And then they given some parameter like duty cycle, and according to my IDP, according to my ID frequency, this display will be on for TAs at the okay, and then lastly they given 3 different values of capacitor: 15 microfarad to 15 microfarad for 17 microfarad. Include any additional sequence and combination logic components as needed to ensure okay, proving appropriate reasoning the selectioning those component. Okay. According to my ID, P equal 34. Given duty cycle 100 minus P, that means 66% duty cycle. Frequency according to my ID 12 hours. Time period according to my ID 83.3 millisecond. Now we know that on and off times. If we know that duty cycle and time period, then we just into that 55 millisecond, and TL equal 28.3 millisecond. 555 stable equation, we know that T is equal 0.693 R1 plus R2 into C. Then TL equal C. Then we ratio to equation T is TL equal R1 plus R2 by R. Then after calculation we get R1 equal 0.94 R2. Here our purpose is anyway find out R2. Here they given three different capacitor. First of all, I checked 215 micro ohm. According to above equation, R2 equal 164 ohm. R1 is 154 ohm, and both are one both are less 1 kilo ohm. Current becomes large, not recommended for 555. That means we know that from Ohm's law, resistor if high current if resistor high current low, if resistor low current high. That means we have to select a resistor that value is 1k or more. If we select a resistor that 1k less, then it is harmful our stable and monostable circuit. So we careful for select which resistor I used in my circuit. Now if I consider 417 micro ohm, R2 equal 87 ohm, R1 equal 82 ohm, even more smaller, definitely not. I need to a capacitor that has resistor value nearby 1k or 1000 ohm. Finally, we check our destination or our final capacitor 15 micro ohm, and I calculate then R2 equal 820 and R1 equal 820 and F equal 12 Hz, and due to cycle calculate TH by T and T equal TL by TH, we calculated 66%, and which is similar to my according to my ID DDR value in TH 57 ms per millisecond, TL 28 millisecond. TH 57 millisecond or TL 28 millisecond, that means is a circuit is blinking ratio or on off ratio. A circuit is connected time 100 second, then 57 second is on and 28 second is off. It is indicated that is nothing else. Then I need to calculate total period. I know that according to my DNC courses, T equals 0.9693 R1 plus R2 to R2 into C, and we calculate R2 equal T by 0.693 into 2.94 into C. Why we find out R2, why not R1? Because R2 controls on and off time separately, while R1 only affects on time. So in 555 stable design must choose C first. Find R2 using requirement, then calculate R1 using duty cycle. Now I trying each allowed given capacitor 15 micro ohm, 215 micro ohm, 417 micro ohm. Then I calculate my DCR R2 from 15 micro ohm is 888, nearby 820 for my according to my ID's values are same in R1 820 nearby same standard value, and we know that and calculate TH by TH or on time value 56.7 millisecond and TL by off time 28.4 millisecond, and we add some that 55.856 millisecond, and we can say 11.7 hertz, and it is similar to, according to my ID, 12 hertz. And due to cycle, we know that T is by T, and T is 56.8, T equal TL by T is 85.2, and average value 66.7%. That is very close to equal my, according to my ID, 12 hours 66% duty cycle. That's why three different capacitor from I choose 15 micro ohm from protect my stable and unstable circuit. And here I showing that stable and unstable circuit. Uh, circuit stable circuit stable circuit using for showing is using for basically blinking, and unstable circuit using for basically gate close open. That means gate control. Now third question rise, we see that, okay, question question they say that third question, prepare a FSM but finite state machine design that output A or TS millisecond. Okay, here the clock period is 1 millisecond. Okay, show the state diagram, state table, and Verilog HDL code only for output A and B. Note that if T is greater than 4 and set T is equal 4, okay, and T L greater than 4, that T L. Okay, now I going to my original circuit. Okay, now it is my third question solution. Here the clock period is 1 millisecond. Output A is for TS and B for TL. Given condition is TS greater than 4, T is 4, TL greater than 4, or TL equal 4, or capacitor equal 15 microfarad. We are using T is 55 millisecond and TL 28 millisecond. Therefore, T is equal 4, TL equal 4, according to above condition. First of all, we need to know here is what is my goal. A control sequence where two output A and B toggle based on a specific timing requirement derive my ID. Define the system. Now we are using for finite state machine design S0 and S1, wherein S0 A1 equal 1 and B equal 0, that stays for 4 clock cycle. S1 equal 0 and B1 equal 1, that stays for 4 clock cycle. There will be toggle in every 4 cycle. Here, to achieve the 4 ms timing, I have implemented a 2-bit counter. Machine stays In S not for counter 01 and S1 01. Once counter reaches 3, it transition to S1. Now analysis the state table. S not presents true for the counter value 0 to 2. That means next state S not 1 0. The loop, and it is, we see that next value S not counter value 1, next state S not 1 0. Now S not equal current state S not counter value 2 S not 1 0. S not current value then 2 S not 1 0. S not counter current value S not counter value 3, next state S1 1 0. Current state S1 counter value 0, next state S1 0 1 output. Then current state S1 counter value 1, next state S1 output 0 1. Okay, and it is my state diagram. S0 to S1, S2, S3, S4, S5, S6, S7, and continuous process repeated. It is a tabular from here. I showing that, and is a very left ADI code. Module FSN blink bracket input clock RST output reg RAG A reg B RAG 2:0 count RAG state LOS post-tech clock or post-tech RST begin. If RST begin state less than or equal 0, counter less than or equal 0, A less than or equal 0, B less than or equal 0, and else begin count less than or equal count plus plus. If count equal begin state less than or equal equivalent state, A less than or equal equivalent A, B less than or equal equivalent B, int, then module, in module, and ending. Lastly, I elaborately discuss on drawbacks or limitation of part 1 and part 2, counter plus parking control logic. Present design supports only a fixed small capacity, that means 6 car. 2. It is a limitation. Counter is any 3 bits, so maximum count is 0 to 7, not suitable for large parking lots. 3 system only tell full or space available, it does not show how many space are left. 4. No error detection or multi-floor large parking system. Where we use 555 timers for display blinking. 1. Timing depends on register and capacitor selection. So for a different capacity or blinking speed, we must redesign values. Only 2 messages are displayed, no numerical indication. 3. If parking capacity increases, timer duty cycle and frequency may need to be recalculated. It is also a barrier, big barrier. Then 4. Circuit becomes bigger if more conditions, less messages are required. It is a barrier. Then modification, if you want this system for larger parking area, more than 6, we have to make some changes. 1. Increases counter bit size. 3 bit count equal max 0 to 7. For 15 cars, 6-bit counter equals 64. Or we think that 100 plus cars, 7 or 8-bit counter use a bigger register and comparator at 7 segment display to show exact free space like space equal 12 or space equal 13 instead of only blinking. For more reliable sensor, I can add automatic gate control and buzzer for full warning. Impact of this modification on this system. A circuit size and number of flip-flops will increases. The comparator and decoder logic will become larger. Theory cost slightly increases, but system is scalable. For system becomes more realistic and usable for commercial parking area. 5. Response time and working principle remain the same, only size expands. Okay. Now I making a demonstrated video for my the digital parking system.
You ever stop and think about the hidden genius behind the most kind of boring things? Well, today we're going to crack open a piece of technology. You ever stop and think about the hidden genius behind the most kind of boring things?
Okay.
Well, today we're going to construct it piece by piece, and we're using a universal digital parking system. You can see all the pieces, the logic, sensors, and timers all working together. So how does it know? How does it know the exact moment that very last spot gets taken? That's what we're about to find out. And this is our roadmap. This diagram shows the whole shebang, a complete professional digital parking system. You can see all the pieces, the entry, the exit, the counter, the timers, the signs. Now it looks pretty complicated, I know, but we're going to break it all down by following the plan. Absolutely love this. On the left, you've got the polished official diagram, all clean and neat. But on the right, that's the real starting point. That's a student's actual handwritten sketch. It's a block diagram that takes the problem and chops it up into logical chunks. You can see the comparator, the timers. This is where the magic really happens, turning an idea into an actual concrete plan. Does that over and over and over again. Okay, so that logic is pretty straightforward. But what are the actual digital parts doing all the heavy lifting here? Let's meet the key players inside this little machine. X is the key. It's the magic number that the entire system is built around. First up, meet the counter. You can think of this thing as the system's bouncer, just meticulously keeping a head count at the door. It's a special circuit made of these tiny electronic switches called flip-flops. Imagine a row of lights. All right, next up we have the comparator. So if the counter is the bouncer, the comparator is the decision maker. It has one very simple but very important job. It takes two numbers, the current count from our bouncer and the stored maximum capacity, which we know is 6, and it just asks one question over and over. Are these two numbers the same? And here's the circuit that makes that big decision. Don't let all those symbols in the diagram scare you. All they really are is a bunch of simple logic gates, tiny little yes or no machines. When you wire them up just like this, they produce a single signal. And in this case, that yes signal only comes out when the current count equals the max capacity. That one little yes is what ultimately flips on the full sign. Okay, so now we know how the full sign gets turned on. But what about the space available sign? And more importantly, why does it blink? Well, the secret is that there are actually two separate timer circuits. Timer 1 is for the full sign. When the comparator shouts that the garage is full, this timer gets the signal and just turns the sign on. To be, well, unstable. It can't be incredibly precise about this. This wasn't just some random blinking. The assignment required a very specific rhythm. The sign had to blink at 12 hertz. What makes all this possible is an absolute legend in the world of electronics, the 555 timer chip. This diagram shows the two timers used. It's awesome. But how does a project like this make the jump into the real world? Well, the very first step is a good, healthy dose of reality. And the student, Shihab Kabir, provides it himself right in his project analysis. He's super clear about it. This design has some major limitations, as he pointed out. So, besides the tiny capacity, the system is just too simple, you know? It doesn't tell you how it's just an opportunity for an upgrade. To handle more cars, you just give the counter a bigger brain. Increase its bit size. Want to be more helpful? Add a display that shows the exact number of free spots. For reliability, you swap in better sensors, and if you want to get really fancy, logic we just walked through. It really makes you wonder, doesn't it? What other everyday objects are out there, quietly doing complex math, running through little logical loops and making decisions for us, all happening right under our noses?